When heating the domains in spin ices to flip spins, is that done in any particular way? Is that done in a uniform way, and you're just hoping that, you know, the ones that don't cancel each other out will move the spins further away from each other, or how does that work?
Yeah, that's a great question, actually. So all we do is, there just is some temperature that's not zero, so you have these magnetic monopoles there naturally. You should expect the concentration to go up as temperature goes up. It's a random process, but yeah, you would expect sometimes you'll create a pair and they'll happen to wander apart. Now, just like if you apply an electric field to an electron, it accelerates the electron. We expect that if you apply a magnetic field to these spin ices, you should accelerate the magnetic monopoles. You have to get the direction right, but that should work. So we have some other experimental tests that are going on now. I should say there's lots of more theory and experiment to be done here. And one of those tests is checking this idea that you apply the field and you'll see the monopoles separate like that. So you can sort of control that to some extent. We can't really go in and flip single spins. We just wait for it to happen, basically, and see. Trying to think of ways to address single spins is one thing we tried to think about, but we haven't made much progress on that. That would be the ideal, then we can really show these things. But yeah, so there's some control over it, but some just measuring what's there already.
Hi. If you find these monopoles, have you basically just disproved one of Maxwell's equations?
Yeah, that's a good question. No, not with these emergent magnetic monopoles. So the Maxwell equation, div B equals 0, is telling us that magnetic charge doesn't exist. Now, if we were to find a fundamental monopole that was a magnetic charge, then we would have to change Maxwell's equations. They're ultimately empirical observations, right? So it's that Maxwell equation just encodes the fact that we've never seen a magnetic charge. If we did see one, we would change it. And that's part of this nice, when I refer to a list of things where we compare electricity and magnetism, we can think of Maxwell's equations as that list. And then we have this one equation where they don't agree. We have a divergence of the electric field given by electrons, say, but we don't have a divergence of the magnetic field. So then we need to update it. But there are other forms of monopoles, like Dirac's monopoles, where you can preserve Maxwell's theory as well. So it's a matter of seeing what's out there, I suppose. But in terms of these emergent magnetic monopoles, it doesn't violate Maxwell's equations. Thanks.
Yes, hi. I'm interested in the monopole and your computation for logic. And obviously, there's a lot of talk about quantum computers. Is this already what you're going through, seen as part of that new generation?
Right. Probably not. And I should say that the stuff with carrying out computations is not something I've worked on, but actually I do have links on my website if you want to take a look. So there's some very nice work there. So far as I know, this would all be classical stuff. So I've talked a little bit about quantum tonight. Really, these magnetic monopoles and spin ices, as we know them, seem to be entirely classical objects at the moment. Now, there are different materials which are candidate quantum spin ices, and then these things would be like quantum magnetic monopoles. But I don't think there's an idea to do quantum computation with them. So this would be more classical computation. But a question I also get asked sometimes is there like a competition between these new types of classical computation and quantum computation, and which one will win? Well, I'd say they're probably not in competition with each other, they'll supplement each other. So you're never going to have a quantum computer on your, well, I speak too soon probably, but you're never going to have a quantum computer as a laptop. You're always going to have to cool it down and make it very clean and so on. So it's going to be more like cloud computing, that sort of thing. But more efficient classical computers are things you could carry around with you, I think. So they probably supplement one another, would be my thought. Thanks.
So thank you very much. That was a lovely talk.
Thank you.
I was just wondering if you could tell us more about the properties of the material that allow it to become a spin ice. So, for example, you mentioned that they had to be tetrahedra so that they observe this 2 in, 2 out. And within a cube, you can embed 2 tetrahedra, so you could have 4 in, 4 out. And how do these shapes perhaps change how long one of these sort of loops can last in terms of time or stability?
Right, that's a very good question. There's loads of stuff I didn't talk about, which I'd have liked to. There is a trick to these tetrahedra, and I think the basic element of the trick is that the tetrahedra are made up of triangles on their faces. So if you think of a face of a tetrahedron, it's a triangle, and it has these spins sat on the corners. So there's a broader, something else that's going on in this problem, which is what's called geometrical frustration. So if we imagine that we have 3 of these spins, these little magnets, and say they're forced to, for example, all point up, but they can flip. So we'd like to point north towards south, say. Let's say we'd like to anti-align them. So if one points up like this, we'd like the other one to point down like this, okay? So with 3 of them on the triangle, we get into trouble, because with 2 it's fine, we can just make them do this. But then what does the third one do? Does it go like this? Well, if it goes like this, it disagrees with that one, because we want to anti-align them. If it instead goes like this, it disagrees with this one. So it's those triangles that lead to this geometrical frustration. And what that means is that these spins can't simultaneously minimize their energies. They have to reach some kind of compromise. And the compromise they reach is that 2 in, 2 out pattern. So you can look at it as, while it's the lowest energy state, it's actually not a great state. In other cases, it would like to do something else. It would like to form something like a ferromagnet where they all line up. So it's that frustration caused by the triangles making up the faces of the tetrahedra that cause this situation to come about. Another way to look at what's going on is that there's a huge number of different lowest energy states. It's, to give it a very fancy name, it's a macroscopic ground state degeneracy. So as long as you have 2 in, 2 out on every tetrahedron, and there's 6 ways to do that per tetrahedron, as long as you have that, you are in one of the lowest energy states. And there's a huge number of ways to do that. So it's that degeneracy, that number of ways of doing things, that ultimately leads to this story of these magnetic monopoles. In particular, it leads to them being what you might call delocalized. You can separate them out from each other, and that's the trick. So there is something a bit special about these tetrahedra. There are other systems that have similar sorts of things going on, or we think they do, but they all should involve triangles in one way or another. So yeah, good observation.
Dysprosium titanate is quite an obscure substance. And do you have other promising crystals that perhaps are more readily scalable?
Yeah, good question. Well, no, the only other one we have so far is holmium titanate, which also sounds pretty obscure. Searching for new ones is a big thing. I actually asked Prabhakaran why did someone grow dysprosium titanate and find this. I forget his answer, actually. People grow whatever, and let's just see what's in there, and we'll try and explain it. So there are 2 known spin ices now. Actually, some people are starting to argue for some other things, but they're all equally obscure at the moment. Quantum spin ices, as I mentioned before, that's a really big thing in this field, people trying to find quantum versions. And they need slightly different properties, but the same basic idea. And there are some candidates for that, but trying to prove that you have quantum spin ices is even harder. That's something people are doing. But again, it tends to be they're pretty weird stuff. They're made of these rare earth elements. I'm not sure if it has to be the case. But yeah, no, I don't know of any non-obscure ones, sorry.
Thank you for a fascinating and entertaining talk. I was tickled by the idea of magnetricity, and I wondered if you and your colleagues over drinks had really discussed what life would be like if you could, plug into the wall and get magnet power. I'm not describing it well.
Right, yeah. So I think I should credit the person who came up with this. I believe Steve Bramwell in UCL here in London came up with the phrase magnetricity, and it's a great phrase. There's a little bit of a limit to it, which is that you can't have a DC current of these magnetic monopoles. You can only have them in AC, but it's not too much of a limitation. But in answer to your actual question, I haven't really thought about what we could do with those magnetic currents. As I said, we're not going to be doing them on a big scale anytime soon, or probably at all. But on the smaller scale, it could be of some use potentially. But I think we're thinking more along the lines of electronics rather than electrical type things. But in principle, you can make anything that works, any electrical thing which works with AC currents could in principle now be made with magnetic currents. So, I'd welcome any suggestions, basically, and we'll see what we can do.
If I were to create a magnet made solely out of monopoles, what would its magnetic field look like? Would it have loops? Would it radiate outwards? What if I repeated the experiment with the iron trimmings on the book? What would happen?
So it only has magnetic monopoles, is that the idea? But it has an equal number of each. I guess it depends how you distribute them, really, I suppose. So when I answered the question earlier and said you can sort of accelerate these magnetic monopoles with magnetic fields, ultimately if you do that, what you'd end up with is sort of a load of north pole monopoles on one surface and south poles on the other. But then really all you have is a load of spins aligned, and you just kind of have a bit more of a normal magnet. So you can think of it like a capacitor if you want to think of like an analog to an electrical circuit. But really you just have a lot of spins pointing in the same direction, so then it's a bit more like a traditional magnetic thing. Yeah, it depends how you arrange them. Oh, if it's all north? No, that's not possible. So remember, they can't leave the sample because they're these emergent properties. So you can only create them by flipping a spin, and that creates one north and one south. And of course, we know we can't get a net excess of one or the other, because then we would actually have a net magnetic charge on our sample. So unfortunately, we're trapped to always have one of each. So another phrase, which I think may have been coined by the same person, is rather than electrolyte, a magnetolite. So you can think of it as, in electrolytes, you have lots of sort of positive and negative electric charges that can separate and recombine and so on. And so you can think of these systems as magnetolites with magnetic charges instead. But you're always constrained to have the same amounts of each charge, unfortunately.
Thank you.
Picking up this magnetolite, physically, how far apart would the monopole and anti-monopole be typically in a crystal?
Good question. There's a paper about basically this exact question, the magnetolite paper. In principle, you can separate them as far as you like within the crystal. If you could perfectly control the thing on the atomic scale, you could create your spin ice ground state with all your 2 in, 2 outs everywhere. You can flip a set of spins and separate them out. But in reality, it's going to depend on what the density of the monopoles is, basically. So if it's denser, then on average, it's not so far until you find the opposite charge. So it depends, basically.
But in the experiment you've done so far,
yeah,
are we talking microns or millimeters?
No, it would be much smaller than that. So I can tell you a little bit about the experiment we originally proposed, which was actually to use a nanoscale magnetometry device, so some really small detector of magnetic fields that works on the scale of a few atoms, basically. That was the original hope. And then what you could do in principle, this is crazy theorist speaking now, you can put your detector there, you cool it down so low temperature, to such a low temperature that there's hardly any monopoles, and you wait for one to wander into the detection range and away again. And when we were thinking of that, we were thinking we could potentially get to having about 1 monopole per 50 tetrahedra, something like that. And we thought that would be enough to detect it with these tiny nanoscale magnetometers. Now that turned out not to be a very practical route, basically because you can't cool things down that low. There's sort of technical reasons with doing the experiment. That's the sort of thing people are gearing up to try and do, but it's going to take a few years. So then it would be 1 monopole per 50 tetrahedra, but in general, we're actually at higher densities than that in what we're looking at.
There was one thing that intrigued me, your experimental setups. You've got your experiment surrounded by liquid helium, presumably, and then cooled it down further. And you said it would be destroyed if you had a paramagnetic material going through it. Well, oxygen's paramagnetic, isn't it? So do you have to exclude the oxygen from the detector, otherwise you get lots of white noise?
I don't think it would be destroyed if you had a paramagnet. It's just that if you only put a paramagnet in there, you would detect perfect red noise. So if it's not perfectly red, if it's a bit pink, then hopefully that's a signal for these magnetic monopoles.
Did you exclude all the air from it when you were doing it, is really the question.
Okay, and my answer to that really has to be I didn't do anything. I'm a theorist, and I would not care to speculate on what was actually done, but it was very hard, I imagine. So to highlight something I should maybe have mentioned during the talk, the way the experiment came about was Fran did her simulations, and we had that team of people I mentioned earlier. And Fran gave a talk about the work in a conference in Oxford. And sat in the audience was Professor Seamus Davis, who's now moved to Oxford. And 6 days after that talk, he sent us an email saying, my student Reinecke has built the device, taken the measurements, and confirmed the theory. So that's not a normal timescale for experiments to be done, right? So they're pretty on it, but I don't know how they did it, sorry.
I just wonder if there's going to be a future in doping the materials to restrict the number of monopoles. Would that be a possibility?
There are certain experiments to change the chemical composition and something like doping. But what you're talking about would be more like sort of doping with magnetic charges rather than electric for the thing to work. We don't know how to get the density lower of monopoles, basically. That would be a really great a really important trick. If there's some way to make fewer of them appear at a given temperature, then that would be handy, because then you can lower the density of them, which would be great. We couldn't think of ways to do that. You can sort of think of ways to try and make more, but making fewer is a bit hard. So that would be great. It's something we tried to think about, but so far haven't succeeded in, I think it's safe to say. So yeah, if you have any ideas, please let us know, and that would help us out. Thanks.
Great lecture. Just a question. How far does the analogy go with magnetic currents and electric currents? Like, do they exhibit resistance, inductance? And in terms of the flow, I mean, electricity travels at the speed of light. Does magnetic currents travel at the speed of light as well?
Those are all very good questions. You could, in fact, be the experimentalist carrying out follow-up work right now, because those are basically the questions we're trying to answer. We're trying to look how far those analogies go. Yeah. In funding proposals, I'm phrasing it actually as it's a bit like the theory of the electron and electricity at the turn of the 20th century. I've got this kind of 19th century obsession at the moment, I guess. So, you used to have electric currents, and they had certain properties and certain relations we could measure. I won't go into the details, but they're along the lines of the things you're asking about. And we resolved a lot of those relationships by realizing that electricity was being conveyed by electrons, these fundamental particles. So trying to extend that analogy for magnetic currents is something that we're currently looking into. But I don't have the answers for you right now, but great question.
So two questions that I wonder about. One is, in this crystal of spins in the dysprosium titanate, what makes this, I don't know, to me it looks a bit like a phase transition. The spins make like 3 spins in pointing towards the center and 1 spin away. And the second is, what defines a magnetic monopole here in physics terms? So is it because locally the magnetic field lines really look like as if they were coming off of a pole, or what makes it to be considered as a monopole or quasi-particle?
Right. Good. Very good questions. Let me, can I give a slightly technical answer to the first one? It's not too technical.
Okay. Yeah, please.
So you're right, it looks a bit like a phase transition, but it's not. So actually, dysprosium titanate at higher temperatures is a paramagnet. So one of these things that's not a magnet till you apply a field, then it becomes a magnet. And as you cool it down, say, from 10 Kelvin to 2, if you look at the specific heat, it has a bump in it, like this. So for a phase transition, you'd want to see something like a divergence or a cusp or something, and you don't see that. So really, it actually is a form of paramagnet, but it's what we call a correlated paramagnet. So in a paramagnet, we can sort of think of the spins flipping independently. In the spin-ice state, they still flip, but they do it in a coordinated way, which we think of as, well, the monopoles are the things we should now be measuring. So it's still spin flips, but they have to be correlated and coordinated and such. And the better description, we think, is in terms of these monopoles moving around. So it's actually, it seems not a phase transition. It's sort of connected to the paramagnet case. But you can think of it, it's kind of like that. Below 2 Kelvin, you start getting loads of these monopoles. That's a good description of the problem. And as you cool it down, you get fewer. In terms of why do we call them magnetic monopoles, that is also a good question. The field lines do look very much like you'd see from a monopole. You can actually do it another way. If you take a solenoid, so like a big long coil of wire, and it's very long and very thin, so something a bit like our Faraday coil here, but one coil and thinner, then you have the sort of north pole coming out at one end and going back into the other. It's a big magnet. And you can actually, so there's theories for how electrons would scatter off magnetic monopoles, for example, and those experiments have been done with long solenoids. So the field around the top of the solenoid will actually look like a magnetic monopole pretty much. Of course, there's no divergence of the magnetic field of B, but it's like the rest of it gets funneled down the middle of the solenoid and comes out at the other end. So you can make these things look like magnetic monopoles. And to some extent, that's basically the story you're getting in the spin-ice materials. It's as if they've got a little divergence of magnetization, in fact, rather than the B field. It looks like it all comes out, but it sort of funnels its way down to the south pole somehow, is a loose way of thinking about it, I'd say. So they do look a bit like it. And in fact, if you were to measure the field off one of these monopoles close to the surface, it would actually fall away from it outside the sample, like that of a magnetic monopole. So I think the analogy is pretty decent. Thank you.
If you had a hollow sphere of a magnetic material and the outside surface was magnetized north and the inside surface was magnetized south, could that act in any way like a magnetic monopole?
That's a great question. Now, I thought about this because I got asked this the other day and I had to think a bit about it. So I think you want to think of loads of magnets sort of doing something like this, right, where all the norths point out and all the souths are pointing in. Now, I don't think it would look like a monopole. You think it would, but actually, if you think of the field lines coming off each of the magnets, they have to come out and go back in like this. So I think you're actually going to have them sort of come out and go back in, so it'll average out to not very much overall. So it won't be that the north will just kind of shoot out. So what you'd really like is it to look a bit like a hedgehog in terms of the field lines, right? If this is a monopole, you want the lines of magnetic field to just shoot out like at 90 degrees off the surface. And I think it wouldn't do that, but maybe if you think about it, you might correct me on this, or maybe it's written in Faraday's notebooks here. I'm not sure. But my thought on this is that actually, because of the way the field lines connect up, it wouldn't look like you'd want a monopole to look. I'm pretty sure it shouldn't, but it's a good question and one I've had to think about a little bit. Thank you.
For a fundamental Dirac monopole, what is the magnetic charge of it or magnetic moment? I mean, is it quantized in the same way as electric charges?
Yeah, that's a great question. Yes, they both get quantized at the same time. Let's see. So I should try and explain a little bit why it is that this quantization occurs. Have you heard of the Aharonov-Bohm effect? The Aharonov-Bohm effect is an experiment. Okay, so it is a bit complicated, frankly, and I've tried to explain this in a reasonable way, and maybe I'm not fully understanding it, which is perhaps why it's not easy to explain. But the basic idea is that, all right, let's give it a go, shall we? So you take the two-slit experiment. Have people heard of this famous quantum experiment? And you can do it with electrons. You shoot your electrons through these two little slits, and you get an interference pattern on the screen. And that's exciting because you can turn the intensity down low enough that you're firing single electrons, but somehow you still build up an interference pattern as if it's gone through both slits somehow. Now, if you do it with electrons and you put a solenoid as the partition between the two slits, then you can put a magnetic field through that solenoid. Now, the field out's an effect on the screen, so it shifts the pattern along. So this is pretty weird because you think, well, the electron never goes in the place where the magnetic field is, which is all down the middle of the solenoid, which it's excluded from that region, yet somehow when you change the field, you can shift the pattern, so what's going on? So what we've kind of realized now is that when the electron moves around the magnetic field, when it does a loop, it picks up this phase, and it picks up an additional phase called the geometrical phase, or related to a Berry phase, as it picks up that magnetic flux. And it's this additional phase shift that causes the pattern to shift on the screen. So electrons looping lines of flux can pick up phases. So when you take the Dirac monopoles, you take a monopole-antimonopole pair and you separate them. Now, they have their magnetic field lines diverging out of them, but they also have this sort of line of flux connecting them in the Dirac case. And it's what's called it's a gauge theory. It's unobservable where this line of flux goes, but if you take a surface around one of the monopoles, you must know that it passes through it somehow. So the idea is that you have this line of flux connecting them. It's a mathematical choice as to where it goes, so in some sense it's not real, but it can have these consequences, which is that, say the flux is here, you move an electron around it, well, the electron picks up a phase, but it has to be unobservable because I could choose where I wanted to put my string connecting the two monopoles. So if it's unobservable, that means that it must be a phase of 2 pi. So you end up with a condition that says that 2 pi is some product of the electric charge and magnetic charge. So this gives you your quantization of electric and magnetic charges. And the fact that you can't observe it means that if there's one in the universe anywhere, well, the Dirac string, as it's called, has to sort of tether to infinity off outside the observable universe or an anti-monopole, and that causes the quantization. So it's well defined in terms of the two giving a product which gives 2 pi. How do they do?
Very much.
was it Lucy? It's pretty tricky, but Dirac was a clever guy. I can't.
So this will be a bit of a change of tone from the rather more technical questions over there. But you use the various different colors of noise at varying points throughout the talk. What actually are the formal definitions for these different colors? So when you say it's perfect red noise,
right.
What does that actually mean?
Great question. Let's have a look. So here's red noise. So the thing we want to measure is want to look at is the noise spectral density. which is, if you've done any sort of signals analysis stuff, it's like the power spectral density. And with red noise, the noise spectral density goes as 1 over the frequency squared well, actually at all frequencies. With these magnetic monopoles, what we get is we get a low frequency plateau where it's a high noise, and then there's a turn off at a certain frequency, and then we get a power law. And if it were a paramagnet, we'd expect to see an inverse square law. Pink noise is 1 over F noise, it's also called. Actually, also it sometimes gets called flicker noise, which is quite exciting because that's my surname. I thought I'd better try and write some papers with that in, and then maybe people will make the mistake and think I had something to do with it, which I didn't. So that pink noise would be 1 over F. Red noise actually I think is also called brown noise or Brownian noise because it corresponds to Brownian motion as well. White noise is flat, constant noise spectral density, and then blue noise is proportional to F, and violet is proportional to F squared. So that's the kind of technical answer. So they're kind of well-defined distributions, basically. Thanks.
You know the one about the ball with it being south inside, north outside?
Yes.
Couldn't you have like maybe a bar magnet where the top half of it is north, the bottom half is south? Couldn't you bend it round into like a Mobius strip where the whole thing would be one side? And if you squished the two ends together, then wouldn't that make it one magnet and it would only have one side? So wouldn't that have to make it...
Yeah, should we have a round of applause for that question? I don't know off the top of my head. We're going to have to try it. We'll have to get a strip of paper and try colouring the sides, so we can do it afterwards. Let's see. That's a great question. I think, we're not going to make magnetic monopoles, probably, but maybe you've found out how to do it. I don't know the answer. You've got me, sorry.
Excellent. Well, on that note, let us give a huge round of applause and thank you to Felix Flicker.